Welcome back to Basic Electronics. In this class, we will start our discussion of Bode plots, which are a convenient way to depict information about a transfer function. We will begin with the unit decibel, which is used in Bode plots. After that, we will consider a simple transfer function and see what is the most meaningful way to show its magnitude and phase as a function of frequency. So let us get started. We are now going to look at how to plot things like gain of an amplifier as a function of frequency. And before we do that, it is useful to look at this unit called decibel, or dB in short. The unit dB is used to represent quantities on a logarithmic scale as opposed to a linear scale. Because of the log scale, dB is convenient for representing numbers that vary in a wide range. For example, a quantity that varies from 0.1 to 10 raised to 5. Also, log scaling roughly corresponds to human perception of sound and light. We respond to sound or light intensities varying over a wide range. And the dB unit makes things very convenient because it uses logarithmic scale, and that allows multiply and divide operations to be replaced by plus and minus, which is much simpler. The unit Bell was developed in the 1920s by Bell Labs engineers, and in those days telephony was the most important technology around, and the Bell Labs engineers wanted to quantify attenuation of an audio signal over 1 mile of cable. So to describe that attenuation, they came up with this unit called Bell. And of course, it is in honor of Alexander Graham Bell, the inventor of telephone. Here are some curious facts about Alexander Graham Bell. He invented the telephone in 1876. He could never talk to his wife on the phone because she could not hear. Bell considered the telephone to be an intrusion and refused to put one in his office. Alright, now the unit Bell turned out to be too large for use in practice, and therefore what is commonly used in practice is 1/10 of a bell, that is called decibel or dB. So the dB is a unit that describes a quantity on a log scale, and it is always with respect to a reference quantity. So if we have a quantity called x, we will say that x in dB is 10 times log to the base 10 x divided by x reference. Let's take an example. Let's say we have some power called P1, and that is 20 watts, and we have a reference power called Pref, that is 1 watt. So P1 in dB would then be 10 log to the base 10 P1, which is 20 watts, divided by Pref, which is 1 watt. So that is 10 log to the base 10 20. That comes out to be 13 dB. Now the gain of a voltage to voltage amplifier is often expressed in dB, and in that case we don't use VO by Vref, we use VO squared by Vref squared, and Vref in that case is the input voltage. And why do we use squares? That is because power goes as voltage squared or current squared for a resistor. So voltage gain in dB would be 10 log to the base 10 VO by Vi squared, that is equal to 20 log to the base 10 VO by Vi, and this of course is a magnitude. There is another unit called dBm, and that is used to describe voltages when we have a reference voltage of 1 millivolt. So this milli is what this M stands for. Let's take an example. Say we have a voltage of 2.2 volts and we want to express that in dBm. That would be 20 log to the base 10, 2.2 volts divided by 1 millivolt. So that turns out to be 6.85 dBm. Let's take an example to get used to these dB calculations. Here is an amplifier with input Vi and output Vo, and these are sinusoidal. Vi cap and Vo cap are the input and output amplitudes. If Vi cap is 2.5 millivolts and the gain of this amplifier, the voltage to voltage gain, is given to be 36.3 dB, then we want to compute Vo cap both in dBm as well as in millivolts. So let us see how to do that. There are two ways of doing it. One, we start with Vi cap, convert that into dBm. How do we do that? 20 log to the base 10 Vi cap, which is 2.5 millivolts, divided by 1 millivolt, and that turns out to be 7.96 dBm. Now we know that Vo cap is Av times Vi cap. We can divide both of these by 1 millivolt. Then we can take log to the base 10 and then we can multiply both sides by 20. And then this right hand side can be written as 20 log to the base 10 Av plus 20 log to the base 10 Vi cap divided by 1 millivolt. Basically, this is a product of two numbers. One is Av, the other one is Vi cap by 1 millivolt, and that is how we get this relationship. And therefore, we can calculate Vo cap now. This number would be Vo cap in dBm. We already have this number given to us, 36.3 dB. This we have computed, that is Vi cap in dBm. So 36.3 plus 7.96, that is 44.22 dBm. So that is Vo cap in the unit of dBm. Now we want to get it in millivolts. We know that Vo cap in dBm is nothing but 20 log to the base 10 Vo cap divided by 1 millivolt. So from this we can get this inverse relationship, that is Vo cap equal to 10 raised to x times 1 millivolt, where x is 1 by 20 times Vo cap in dBm. You should verify that this indeed follows from this definition. And then we are all set. We can now find Vo cap in millivolts. So the answer turns out to be 162.5 millivolts. Let us look at method 2 now. We know that Av is 36.3 dB. We can convert that into a real number, which is the ratio of Vo and Vi, the magnitude of the ratio. So what we know is 20 log to the base 10 of Av is 36.3, and from that we get Av equal to 65. And now we know Vi cap 2.5 millivolts, we know Av 65, therefore Vo cap is 162.5 millivolts. And once we have Vo cap in millivolts, we can find Vo cap in dBm using 20 log to the base 10 Vo cap divided by 1 millivolt, and that comes to 44.2 dBm. Let us now look at the unit dB as it is used in audio measurements. Now a sound wave corresponds to a certain air pressure, say P. Now to convert this pressure into dB, we need a reference pressure. That reference pressure is 20 micropascals. And why is this number chosen? Because that happens to be our hearing threshold. We don't hear things if that pressure is less than this number. So now the pressure that actually corresponds to the sound wave that we are talking about can be expressed in dB using this familiar expression 20 log to the base 10 P divided by P reference. Here are some interesting and useful numbers. 0 dB corresponds to a mosquito buzzing around about 3 meters from a person, and this of course assumes that that person is in a soundproof room with no other sounds around. So that is about our threshold, hearing threshold. A whisper is 20 dB. Normal conversation 60 to 70 dB. Noisy factory 90 to 100 dB. Loud thunder is 110 dB. Loudest sound that we can hear or we can tolerate is 120 dB. If the sound is louder than this level, then our ears can get damaged. And if we go on jacking up the dB level, then at some point windows shatter, glass breaks. That is at 163 dB. And of course there are laws about the dB levels. In India, these laws are governed by the Ministry of Environment and Forests, and you will find these numbers on their website. So these are the daytime dB levels. Industrial area, the sound is not supposed to be louder than 75 dB. Commercial area 65 dB. Residential area 55 dB. And silence zone such as a hospital 50 dB. Okay, with that longish introduction, let us now come to Bode plots, the topic of our interest. Here is a black box with a transfer function h of s. And what is h of s? H of s is Vo of s divided by Vi of s. S here is the Laplace variable, and for our case it is j times omega. And here is an example of h of s. Say it can be k divided by 1 plus s tau, where k is some constant and tau is some time constant, and that is the same as k divided by 1 plus j omega tau, because s is equal to j omega. Now h of j omega is a complex number as shown in this example, and a complete description of h of j omega therefore will involve two plots. One is a plot of magnitude of h of j omega versus omega, and second a plot of the phase of h of j omega versus omega. This first plot is called the Bode magnitude plot, and the second one is called Bode phase plot. Bode gave simple rules which allow construction of the above plots in an approximate or asymptotic manner, and we will see several examples of these plots. Let us start with this simple transfer function of a series RC circuit. The capacitance presents an impedance which is 1 over j omega c, and in terms of the Laplace variable it is 1 over sc. So VO in this case is this impedance divided by the sum of these two by voltage division times Vs, and of course we are talking about sinusoidal steady state. So that is 1 over sc divided by R plus 1 over sc times Vs, and these now are phasors, both Vo and Vs. So the transfer function, which is defined as Vo divided by Vs, is 1 divided by 1 plus SRC. This simply follows from this expression. We multiply both numerator and denominator by SC. In the numerator we get 1, in the denominator we get 1 plus R times SC. So that is this expression. And we can now substitute for S j times omega. So we get 1 divided by 1 plus j omega RC, and that we can rewrite as 1 plus j omega by omega 0, where omega 0 is 1 over RC. So that is the transfer function for this series RC circuit. Let us make a few comments about this transfer function. First, the circuit behaves like a low pass filter. What does it mean? That means it will pass input voltages with low frequencies without any attenuation or reduction in the magnitude, whereas high frequencies will get blocked. That means if the input voltage has a high frequency, it will appear attenuated or reduced at the output side. And why does it behave like a low pass filter? Let us take a look. For omega much smaller than omega 0, this is the low frequency region now, the transfer function is approximately 1 because this component is very small compared to 1. So therefore there is no reduction in VO. So VO and VS are nearly equal. What about omega much larger than omega 0? Then this 1 is small compared to this term, and our transfer function then is approximately 1 divided by j omega over omega 0, like that. And omega 0 is a constant. When we take magnitude of this h of j omega, we get h of j omega proportional to 1 over omega. What does it mean? That means if we go on increasing omega, the magnitude of h of j omega goes on decreasing. So that means the output voltage is much smaller than the input voltage in magnitude. Let us note that this h of j omega could also be written as simply h of omega, but this is a more commonly used convention in textbooks, especially in control systems. So we will stay with this notation. Alright, next point. Let us now look at the magnitude and phase of h of j omega. What is h of j omega? It's here. It is of the form numerator divided by denominator, and the magnitude is the magnitude of the numerator, which is 1, divided by the magnitude of the denominator, and that is the square root of the square of the real part, that is 1, plus the square of the imaginary part, that is omega by omega 0. So that is what we get for the magnitude. What about the phase? The phase of h of j omega is the phase of the numerator, in this case 0 degrees, minus the phase of the denominator, in this case tan inverse omega by omega 0. So the net result is the phase or angle of h of j omega is minus tan inverse omega by omega 0. Next point, we are generally interested in a large variation in omega and its effect on the magnitude of h and the angle of h. And what do we mean by large over here? By large we mean several orders of magnitude. For example, we may be interested in omega varying from 0.1 radian per second to 10 raised to 6 radians per second. As omega varies over a wide range, the magnitude of h, that is mod h, will also vary by orders of magnitude. And here is an example. We have mod h proportional to 1 over omega here, and if omega changes by several orders of magnitude, mod h will also change by several orders. On the other hand, the phase, that is angle of h, varies in a limited range. Let us look at this example. We have angle h given by minus tan inverse omega by omega 0. If omega is much smaller than omega 0, then this number is close to 0, and then the angle h is about 0 degrees or 0 radians. What if omega is much larger than omega 0? Then omega by omega 0 is a large number, and in the limiting case it could be infinity, and then the angle will tend to minus 90 degrees or minus pi by 2. And these are important observations that we should keep in mind. They will help us when we want to plot mod of h and angle of h as a function of frequency. Let us now look at how h varies versus omega, and that is given by this relationship. We are talking about the magnitude of h right now. Here is a plot. The x-axis is omega in radian per second. This is omega equal to 0. This is omega equal to 10 raised to 6. And the y-axis is mod of h. And as we have seen in the last slide, mod of h approaches 1 if omega is small, because this term is negligible compared to 1. That is what we see over here. As omega increases, mod of h goes as 1 over omega. So as omega goes on increasing, mod of h goes on decreasing, and it appears like 0 here in this plot. Now this kind of plot is not very useful because we can't distinguish between the mod of h values at different frequencies, and clearly some improvement is required. So let us see what that is. Here is an improved plot. What is the difference between these two plots? Here we have a log axis. So mod of h is 10 raised to 0 here, 10 raised to minus 1 here, 10 raised to minus 2, and so on. And definitely we can resolve mod of h better now with this log scale. For example, let us take omega equal to 2 times 10 raised to 5 radians per second, that is here. And now we can read the value of mod of h from this curve. So somewhere there. What is that value? So this is 2 10 raised to minus 3, 3, 4, and let's say it's 5. So something like 5 times 10 raised to minus 3. This was not possible to do in this older plot because the y scale had also got compressed here. Alright, so definitely some improvement, but we do need further improvement because our lower frequencies have still got crowded here. For example, we cannot tell the difference between omega equal to 10 raised to 2 and omega equal to 10 raised to 3 radians per second. So that calls for some more improvement. Let us see what that is. What can be done is to replace the linear x-axis with a logarithmic x-axis as shown in this figure. This is omega equal to 10 raised to 0, 10 raised to 1, 10 raised to 2, and so on. And now we can very clearly, easily distinguish between different frequencies. And now it is easy to read the mod of h value for a given frequency. For example, 10 raised to 2, it is 1, 10 raised to 3, it is something like maybe 7 times 10 raised to minus 1, etc. Apart from that, when we plot mod of h versus omega in this log fashion, certain trends become very clearly visible. Let us see what those are. At low frequencies, we find that mod of h becomes constant, equal to 10 raised to 0 or 1. And at high frequencies, we see that mod of h falls as omega increases. And in fact, these two regions, the high frequency part and the low frequency part, meet at omega equal to omega 0. So that indicates the boundary between these two regions. What is omega 0? 1 over RC. R is 1K, C is 1 micro, so RC is 1 milli. So omega 0 is 1 over 1 milli, which is 10 raised to 3 radians per second. So that is what omega 0 is. Apart from that, we can also make out the dependence of mod of h on omega in this high frequency region. For example, let us say we have increased omega from 10 raised to 4 to 10 raised to 5 radians per second. At 10 raised to 4 we are here, 10 raised to 5 we are here. What has happened to mod of h? Mod of h was 10 raised to minus 1. It has now gone down to 10 raised to minus 2. So we have increased the frequency by a factor of 10 and mod of h has decreased by the same factor, 10 raised to minus 1 to 10 raised to minus 2. So therefore we can conclude that mod of h is varying as 1 over omega in this region here. So this log-log plot is very useful and is indeed very commonly used in practice. To summarize, since omega and mod h vary by several orders of magnitude each, a linear omega axis or a linear mod h axis is not appropriate, and therefore what is done is log of mod h is plotted against log omega. Now what we have done here essentially is the same as plotting log mod h versus log omega. We have used axes here which are logarithmic, but instead of that we could actually calculate log of mod h and log omega for each data point and then plot those on a linear scale. That amounts to the same thing as what we have done here. Alright, let us now see what happens if instead of plotting mod h on a log scale like we did before, we plot mod h in dB on a linear scale. This is a linear scale, 0, minus 20, minus 40, minus 60, etc. And what we see is that the shape of the plot does not change. This shape is identical to that shape. And of course there is a very good reason for that. That is, mod h in dB is equal to 20 log of mod h, and that is simply a scaled version of log of mod h, scaled by this factor of 20. So there is therefore a one-to-one correspondence between these two graphs. For example, mod h equal to 10 raised to minus 1 here, what does it correspond to? 20 times log of 10 raised to minus 1, which is 20 times minus 1, which is minus 20. So this point is in fact over here, and so on. So therefore the shapes are the same. What has changed is only this axis here. This is a very important point, and in practice we might see plots of this kind or of this kind, and we should immediately recognize that they are in fact identical. Let us now look at what happens if we plot mod h as a function of frequency in hertz rather than frequency in radians per second, as we did earlier. In particular, we have seen that this omega 0 serves as the boundary between the low frequency part of mod h and the high frequency part of mod h. And so let's focus on this boundary as we change the axis from radians per second to hertz. And let's say we keep these numbers the same, that is omega is going from 10 raised to 0 to 10 raised to 6 in this plot, and the frequency in hertz is going from 10 raised to 0 to 10 raised to 6 here in this plot. Alright, so what is the frequency that corresponds to omega 0, which is equal to 10 raised to 3 radians per second? That is f0, and it's given by omega 0 by 2 pi, which is about 159 hertz, let's say 160 hertz. So what will happen as a result is this omega 0 point will now shift to 160. Where is 160? This is 10, this is 100. 160 is somewhere between these two. That is where it is. And this happens to every other frequency point, and therefore the entire mod h versus omega curve shifts, in this case leftward. So here is the summary. Since omega is 2 pi times f, log omega is log of 2 pi plus log of f. And because of this relationship, this is just a constant. Changing from radians per second to hertz only causes a shift in the x direction, but the shape of the plot does not change. Another very important point to remember. Let us now talk about the phase of h as a function of omega. And if you recall, this is the relationship. Angle of h, or the phase of h, is minus tan inverse omega by omega 0. And omega 0 for our example is 10 raised to 3 radians per second. Now the left plot here shows angle of h versus frequency with linear axes. And as we saw in the magnitude case, this plot is also not very useful because the low frequencies have got highly compressed here, and we really can't tell the difference between 10 raised to 2 radians per second and 10 raised to 3 radians per second, for example. And to solve that problem, what we can do is to use a logarithmic frequency axis, and that is what we have done here. And that does the trick. We can now clearly see the behavior of the angle h as a function of frequency. And in this case, there is no real need to change the y-axis or the angle axis to a logarithmic axis, because the angle is only going to change from minus 180 degrees to plus 180 degrees. And it's not going to change by orders of magnitude like in the magnitude case. And as before, when we plot the frequency on a log axis, we can clearly see certain trends as well. For example, at omega equal to omega 0, which is this point here, the phase is minus 45 degrees, and that is something that we expect from here, minus tan inverse omega equal to omega 0. So this is 1, and that is minus tan inverse of 1, which is minus pi by 4 or minus 45 degrees. Also, as omega becomes small, this quantity becomes 0 degrees, that is this part. As omega becomes large, minus tan inverse of infinity approaches minus pi by 2 or minus 90 degrees, that is this part. So from this angle versus log omega plot, we can get a lot of information. To summarize, since angle h varies in a limited range, in this case from 0 degrees to minus 90 degrees, a linear axis is appropriate for the angle. And as in the magnitude plot, we use a log axis for omega since we are interested in a wide range of omega. In this case, from 10 raised to 0 to 10 raised to 6. To summarize, we derived the transfer function h of j omega for a simple circuit. We then looked at the variation of the magnitude of h and the phase of h versus frequency plotted in different ways. We concluded that a log-log plot for the magnitude and linear log plot for the phase are appropriate. In the next class, we will see how to obtain Bode plots for a given h of j omega. So see you next time.